Good morning. We are going to discuss what are donors and acceptors. When a semiconductor is doped with impurities, the semiconductor becomes extrinsic and impurity energy levels are introduced. In the diagram, we show schematically that when a silicon atom is replaced or substituted by an arsenic atom with 5 valence electrons, the arsenic atom forms covalent bonds with its 4 neighboring silicon atoms. The fifth electron has a relatively small binding energy to its host arsenic atom and can be ionized to become a conduction electron at a moderate temperature. We say that this electron has been donated to the conduction band. The arsenic atom is called a donor and the silicon becomes N-type because of the addition of negative charge carrier. Similarly, when a boron atom with 3 valence electrons substitutes for a silicon atom, an additional electron is accepted to form 4 covalent bonds around the boron and a positively charged hole is created in the valence band. This is called a p-type of semiconductor and boron is an acceptor. We can estimate the ionization energy for donor E0 by replacing M0 with electron effective mass Mn and taking into account the semiconductor permittivity epsilon s in the hydrogen atom model by the equation Ed is equal to epsilon 0 by epsilon s whole square Mn by M0 into Eh. This is the equation for ionization energy. The ionization energy for donors measured from conduction band edge as calculated from the given equation is 0.025 electron volts for silicon and 0.007 electron volts for gallium arsenide. The hydrogen atom calculation for ionization level of acceptors is similar to that for donors. We consider the unfilled valence band as a filled band plus a hole in the central force field of negatively charged acceptors. The calculated ionization energy measured from the valence band edge is 0.05 electron volts for both silicon and gallium arsenide. This simple hydrogen model atom, this simple hydrogen atom model cannot account for the details of the ionization energy, particularly for the deep impurity levels in semiconductors, that is with ionization energies greater than or equal to 3 kT. However, the calculated values do predict the correct order of magnitude of the true ionization energies for shallow impurity levels. Figure shows the measured ionization energy for various impurities in silicon and gallium arsenide. It is possible for a single atom to have many energy levels. For example, oxygen in silicon has 2 donor levels and 2 acceptor levels in the forbidden energy band gap. Now we talk about what are non-degenerate semiconductors. We have assumed that the electron or hole concentration is much lower than the effective density of states in the conduction band or the valence band. In other words, the Fermi energy level EF is at least 3 kT above EV or 3 kT below EC. For such cases, the semiconductor is referred to as non-degenerate semiconductor. For shallow donors in silicon and gallium arsenide, there usually is enough thermal energy to support the energy Ed to ionize all donor impurities at room temperature and thus provide the same number of electrons in the conduction band. This condition is called complete ionization. Under a complete ionization condition, we can write the electron density as N is equal to capital ND, where ND is the donor concentration. In the figure, we show complete ionization where the donor level Ed is measured with respect to the bottom of the conduction band and equal concentration of electrons which are mobile and donor ions which are immobile as shown in the diagram. So we obtain the Fermi energy levels in terms of the effective density of states Nc and donor concentration Nd. Ec minus Ef is equal to kT ln brackets Nc by Nd bracket close. Similarly, for shallow acceptors, there is complete ionization. The concentration of holes is P is equal to Na. This is the assumption, where Na is the acceptor concentration. We obtain the corresponding Fermi energy level as EF minus EV is equal to KT ln in brackets Nd by Na bracket close. We can see from the diagram that higher the donor concentration, the smaller the energy difference Ec minus Ef. That is, the Fermi energy level will move closer to the bottom of the conduction band. Similarly, for higher acceptor concentration, the Fermi level will move closer to the top of the valence band. In the diagram, which illustrates the procedure for obtaining the carrier concentration, this figure is similar to the one which we have already seen earlier. However, the Fermi level is closer to the bottom of the conduction band. The electron concentration, which is the upper shaded area, is much larger than the hole concentration, which is a lower shaded area. It is useful to express the electron and hole densities in terms of the intrinsic carrier concentration Ni and the intrinsic Fermi level Ei, since Ei is frequently used as a reference level when discussing the extrinsic semiconductors. So we obtain the equation N is equal to capital Nc exponential in brackets minus in brackets Ec minus Ef bracket close divided by Kt bracket close. This becomes equal to Nc exponential in brackets minus in again brackets Ec minus Ei bracket close divided by Kt bracket close exponential in brackets again another bracket Ef minus Ei bracket close divided by Kt bracket close, or N is equal to Ni exponential in brackets again in brackets Ef minus Ei bracket close divided by Kt bracket close. And similarly, P is equal to Ni exponential in brackets again brackets Ei minus Ef bracket close divided by Kt bracket close. Now if we take the product of N and P, we find that this equals to Ni square. This result is also identical to that for intrinsic case which we have seen earlier. This is called the law of mass action, which is valid for both intrinsic and extrinsic semiconductor under thermal equilibrium condition. In an extrinsic semiconductor, the Fermi level moves either towards the bottom of the conduction band in N-type or towards the top of the valence band in P-type. Either N or P-type carriers will then dominate, but the product of two types of carriers will remain constant at a given temperature. If both types of donors and acceptor impurities are present simultaneously, the impurity that is present in greater concentration determines the type of conductivity in the semiconductor. The Fermi level must adjust itself to preserve the charge neutrality, that is, the total negative charges, the electrons and the ionized acceptors must equal the total positive charges, holes and ionized donors. So, under complete ionization condition, we have Na plus capital Na is equal to P plus Nd as shown in the equation, and if we solve for the equation, the equilibrium electron and hole concentration in an N-type semiconductor turns out to be N is equal to half of within brackets Nd minus Na plus under root of in brackets Nd minus Na whole square plus 4 Ni square bracket close as shown in the equation below. Pn is equal to Ni square by Nn. In an equation, the subscript N refers to N-type of semiconductor. Because the electron is dominant carrier, it is called the majority carrier. The hole in the N-type semiconductor is called the minority carrier. Similarly, we obtain the concentration of holes, the majority carrier, and electrons, which are the minority carriers, in a P-type of semiconductor as in the equation which we have given below. Pp is equal to half of brackets Na minus Nd plus under root of within brackets Nd minus Na whole square plus 4 Ni square bracket close. And similarly, Np is equal to Ni square by Pp. This is from the law of mass action. The subscript P, as we have already mentioned, refers to P-type of semiconductor. Generally, the magnitude of net impurity concentration Nd minus Na is larger than the intrinsic carrier concentration Ni. Therefore, the above relationship can be simplified to N is nearly equal to Nn is equal to Nd minus Na if Nd is greater than Na, and similarly Pp is nearly equal to Na minus Nd if Na is greater than Nd. The equations come together and we can calculate the position of Fermi level as a function of temperature for a given acceptor or donor concentration. A plot of these calculations for silicon and gallium arsenide are shown in the diagram. We have these calculations for silicon and gallium arsenide. We have incorporated the figure of variation of the band gap with temperature. We note that as the temperature increases, the Fermi level approaches the intrinsic level, and that is the semiconductor becomes intrinsic. The figure shows the electron density of silicon as a function of temperature for donor. Concentration of Nd is equal to 10 to the power 15 per centimeter cube. At low temperatures, the thermal energy in the crystal is not sufficient to ionize all the donor impurities present. Some electrons are frozen at the donor level, and the electron density is less than the donor concentration. As the temperature is increased, the condition of complete ionization is reached, that is Nn is equal to Nd. As the temperature is further increased, the electron concentration remains essentially the same over a wide temperature range. This is the extrinsic region. However, as the temperature is increased even further, we reach a point where the intrinsic carrier concentration becomes comparable to the donor concentration. Beyond this point, the semiconductor becomes intrinsic. The temperature at which the semiconductor becomes intrinsic depends upon the impurity concentration at the band gap value, and it can be obtained by setting the impurity concentration equal to Ni. We now discuss what are degenerate semiconductors. When the doping concentration becomes equal or larger than the corresponding effective density of states, we can no longer use the approximation, and the electron density has to be integrated numerically. For very heavily doped N-type or P-type semiconductor, EF will be above EC or below EV. The semiconductor is referred to as a degenerate semiconductor. An important aspect of high doping is the band gap narrowing effect, that is, high impurity concentration causes reduction in the band gap. The band gap reduction delta Eg for silicon at room temperature is given by the equation delta Eg is equal to 22 in brackets n by 10 to the power of 18 bracket close to the power of half milli electron volt. The doping is in centimeter cube inverse. For example, for Nd very much less than 10 to the power of 18 per centimeter cube, delta Eg becomes less than or equal to 0.022 electron volts, which is less than 2% of the original band gap. However, for Nd is greater than or equal to Nc, which is equal to 2.86 into 10 to the power of 19 per centimeter cube, delta Eg is greater than or equal to 0.12 electron volt, which is a significant fraction of Eg. So, at the beginning, we see the changing of temperature or the amount of impurities can drastically vary the conduction of a semiconductor. Thank you.